Okay, so I'm trusting that you did what I asked and watched the first part of the video and then paused to do some thinking on your own, and you will now be more engaged in the rest of this. So this is our problem statement, and I think one of the first things that comes to most people's mind, unless you've thought about these kind of things in the past or you're an above average programmer, is okay, I need to create a time vector. I need to create the input sine wave, which is just in this case a 1 hertz sine wave. Like that's obvious from the plot. So if I have a time vector and like so from 0 to 1 second in steps of 0.01, so it's 100 hertz, and I generate a y vector based on the sine function. What's wrong with just saying if y is greater than 1.5, set it equal to 1.5, and otherwise if y is less than, that should have a negative sign, so that's one thing that's wrong. There's a little typo there. But that's not the biggest issue with this code. What's going to happen if we run this code? Dramatic pause. You're probably not talking to me. Although if this was an episode of, say, Dora the Explorer, you would be. I'll pretend I didn't say that. Okay, so this is saved as badexample.py, or badidea.py. And if I run that, the first thing you see is that the value error, the true value of an array with more than one element, is ambiguous. So that might seem a little weird to you. But so here's y, and y is a vector of 100 values. If I say, so first when Python executes this, it executes this code and then it tries to execute the Boolean value. So y greater than 1.5. NumPy says, oh, you're taking a vector, you're comparing it to a scalar, you must want a vector of Boolean values. And so there's the problem. You're asking for one true-false answer in your if statement, but there's actually 100 answers, and some of them are false, and most of them are false, and some of them are true. So Python simply doesn't know what to do with a vector. And so NumPy has deliberately built in what I think is a reasonably helpful error message if you know what you're asking. And it says the value of an array with more than one element is ambiguous. So if you did have a value where they were all true, there is a function that's y.all, or sorry, this would be a Boolean vector. So if I said bv is equal to that, now I have the vector of those, and so I could say bv.all, and it would say false. I could say bv.any, and it would say true. So it has some true and some false, so they're not all true and they're not all false. But that's really not what we're trying to do in our code. We want to take these values and set y equal to 1.5 then and only then. So I need to know what are the indices of these guys and set y equal to 1.5 at those index values. And then I need to find where y is less than negative 1.5, find the indices of those data points, and set that equal to negative 1.5, y equal to negative 1.5 at those indices, and then I would be done. So there are a couple of different ways to solve this problem, but like I said, I want to first of all do a quick for loop review. Maybe it was just a few students, but on the review, you had something like this. And I think the problem was that there was like an I here, and you were supposed to debug that. And some people said that I must, maybe. Or maybe there was another question that was just a missing colon. And so people were trying to debug this, and they said basically you can't do a for loop like this. But what I want you to see is that if I do that, I can in fact do a for loop exactly like that. And this is one of the things that at first is really counterintuitive if you're coming from a different language, that Python has such a strange looking for loop structure, but it turns out to be really, really powerful. So if I said for item in my list, item equals that, it just works. Every time through the for loop, it switches item to be A, then B, then C, then D, and so you see us printing that out. Some students who are, like I said, coming from other languages where this is not how you do things, wanted to do something like this. And we'll get to this in the enumerate. Whoops. Sorry, now I'm live coding, and that's maybe not super great. So I'm going to do this twice, and so now if I run the for loop example, the first time through it simply prints A, B, C, D because there is no kind of I, because we haven't asked it for one in that scenario. And then instead, the second time through, I specifically ask for I in the range of the length of the list. And so N would be the length of the list. If I defined an N, if it was cleaner, I could do that. Maybe this looks better. So that would run in exactly the same way. And we would see that N is that, and the range of N is 0, 1, 2, and 3. And so each time through, I'm now printing I, and then I am, whoops, screwing that up. So item would then be my list of I. Sorry, I don't know what that strange laugh was, but okay. So now item is A, B, C, and D because I'm explicitly indexing it. And that might not look like a lot different. Mainly it's just one extra line of code, but it's one extra line of code where you could make some kind of syntax error and mess things up. So I think that this is the recommended Python for loop structure, and it's clean and it's easy and it's great. Now the problem is if we were going to then apply this kind of an if-then for loop thing to solve our original problem, we would need to set up a loop that said if y sub I is greater than 1.5, then I want that y value in that vector. I need access to both the current value of y of I as well as the index I. I can't just have y sub I for when I get to the for loop part and want to reassign y of I to equal 1.5, for example. So I can't just say for y sub I in y, because I also, when I want to do the for loop part of the if statement part of it, I need access to y of I. So one way to do this as a for loop and get this to work correctly, we just set up our t and y values just like before. Get an n, and then I'm going to output a y-saturated vector that starts off as a vector of zeros, the same length as y. And then for I in the range of n, I'm saying that y sub I is equal to y of I. If y sub I is greater than 1.5, then my saturated y is equal to 1.5. If y sub I is less than a negative 1.5, then my saturated y is negative y. Otherwise, y saturated is equal to y sub I. So if I run this code, I generate this figure, which is exactly the figure we were trying to generate. You can see that it does its saturation thing correctly. And I have y, and I have y sat, and the biggest thing is you see a bunch of negative 1.5s in here and a bunch of positive 1.5s in here. So that code works, and there's really nothing wrong with this code except that to my mind this is just one more thing you could accidentally make an error on, and so I'm not a super big fan of doing it that way. This is how to use enumerate, and so let's first there's an enumeration review example. So if I had this same list that I had in our for loop example, and now I'm going to use the enumerate function. You'll notice that over here I've got I comma item in enumerate of my list. And so every time through the for loop, I is going to go 0, 1, 2, 3, while item goes A, B, C, D. And so this is automatically doing some of those other things for us. And there's just less code for me to mess up when I'm using enumerate. And so I think that's important. And so if we look at I think I already had this open. The enumerate version of this, so I still create my t and my y vectors just as before. I create my y saturated output vector just as before. but I just used this line, for I comma y sub I in enumerate y. So like I said, I is going to go from 0 to 99, y is going to go from y of 0 to y of 99. Then if y sub I is greater than 1.5, I'm going to do the exact same stuff. Actually, this part of the code is exactly the same as the previous example. The only thing that's different, and like I said, it seems like a really small thing, but I think it just eliminates, is instead of having these two lines, we're now replacing those with this one line. And I think this is less likely for you to make mistakes on. Otherwise, this is exactly the same. And if I run that, I would get exactly the same graph. If it makes you feel better, you think I cheated, I could close the graph. There's no graph. And then run it. I could also put something different in the title. But it looks exactly the same. So that's a pretty good way to do this. But again, I would like to actually, if it were me, get rid of all of this because it's all potentially stuff I could make mistakes on. And so let me remind myself of the different options that we haven't talked about yet. Let's do the cryptic one and then we'll do the where. I think that will be the best way to convince you that where really is the way to go. So I create my t, y, and y sat values exactly as before, and then I plot y. Okay, not exactly as before, sorry. So I make y sat a copy of y. One of the things that will freak you out a little bit if you're not familiar with the idea of copy by reference instead of copy by value, there are other commercially available programs that do data processing type stuff, and when you create a copy of a vector, it automatically duplicates everything in RAM. And that's a really safe way to do it, and it makes it easier for users not to shoot themselves in the foot. But creating new copies of every vector consumes a lot of RAM. Maybe RAM is super cheap now, and we just don't care. But if I just said y sat was equal to y, and then I went in and I made changes to certain elements of y sat, it would make those same changes to y because we didn't make a copy of it. We just said y sat and y both point to the same reference in RAM. So if I want to make a copy, I need to explicitly do so. And so the copy module has a function called copy.copy that makes a specific copy. So now I can make changes to individual parts of y sat without it affecting y. So first, y sat is just a copy of y. And then this crazy little statement here finds that Boolean value we've been talking about of where am I greater than 1.5. And so that's a vector of 100 true and false statements. And NumPy knows how to take that and use it as indices so that I only affect the parts where that is true. And that will do the positive saturation part that we were talking about. And then this will do the negative saturation part where we're talking about. And so if I were to, first of all, close my guy there, and if I said run the cryptic one, you'll see that it generates exactly the same plot. But again, I think that this, if you're super familiar with NumPy, is no big deal. But I think it's a little bit weird if you're new to NumPy, and so I want to introduce you to the where statement. So again, I'm going to create t and y, and I'm going to create y sat as just a copy of y. And I'm going to use the where function. And so inds 1 is going to be where y is greater than 1.5. So let's just first of all run this guy. But just show where is y greater than 1.5. And so those are the indices. Seem to be a lot of those. Oh, for some reason in this example I've changed the dt just to confuse myself. So let me undo that and rerun that. So those are the indices where y is greater than 1.5. Another thing that's slightly weird about this is that NumPy tries very hard to use the n-dimensional array as its base class. And so when you do these kinds of functions, it wants you to allow you to work with arrays of any dimension. So a vector would be a 1D array, a matrix would be a 2D array, but you don't have to stop at 2, and you can just do any number of dimensions. And so it's returning an array, a list of indices for any number of dimensions. But since we are normally doing this just on vectors, I mean, you have to think differently about this if you're trying to do this on a matrix. But if you're just trying to do a vector, then I'm always asking for, give me the zeroth, or the, however you want to, there's not like a, I always say first, but it's index 0. Give me the index 0 list for the dimensions of the 0th, I don't know. I know I have a 1D array. I just need the first or the 0th set of indices coming out of where. And so whenever I use where on a vector, if I know it's a 1D array, I'm just going to put square bracket 0 after it. That's just a weird quirk that you just kind of accept. And so that's the result of calling where and then grabbing the 0th index, which is the same as inds1. And so inds1 is a list of integer indices, and I can then come in here and say, at the indices returned by represented by inds1, set y equal to 1.5. Then I'm going to find where it's less than negative 1.5, and I'm going to set ysat of those indices to negative 1.5. And I'll specifically put in here a title that this is from where function. And so again, I will close that figure, and there is a close function that I'm just not using right now. Bam. And so from the where function, it's exactly the same. Each time through, my ysat ultimately ends up being exactly the same, but I'm specifically using the where function to apply an if statement to a vector and expecting the indices where the condition is satisfied. And if there's ever a spot where I said, so for example, if I said where y is greater than 3, that comes back with an empty array inside this tuple. And so if I asked for that of 0, it would have this 0 length array. And so, for example, if I was writing some kind of data processing thing, I could say, you know, inds3 is equal to that, and I could say assert the len of inds3 is greater than 0, comma, no data matches the where statement. And it would say, well, that's not satisfied. So that would just be one example of how to stick an assert into a data processing function. That might be helpful. All right, thanks.